what do we do before we launch? What is the value of the cal valve? What can we learn? And what is it like? What the cal valve looks like before you launch? Simulations, no observations.
The parameterizations, the retrievals.
You're not supposed to get this.
There we go. Pick it up.
So, for example, if you want, Alessandro, for example, we want to have an algorithm to take this radar reflectivity factor and convert it to snow for 8 millimeters per hour, correct? That means you must have an idea about how those two things are related. So somebody goes measure with a bucket or with an imager, the snowflakes, so it knows how they look like, and measures it with a radar. So it has a radar and the snow amount. And then finds a relationship, and that's the retrieval, correct? In a simple way. So before you could use cal valve because we want to develop the physical basis for an algorithm. If you convert this engineering unit to something geophysical, you have to have it. So cal valve could be for that. Cal valve could be for an airborne demonstrator that looks like the spaceport. Cal valve could be to evaluate different aspects of your simulation. But now you want to do, we're post-launch, correct? EarthCARE launch already. So now we want to focus on what can you do after you launch. So there's something that has changed since we had the NASA A-Train. When the NASA A-Train launch was 2006, I don't know if you was in this business in 2006, but in 2006, we barely had 3 super sites in Europe. The one was in Sirta, outside of Paris. There's Lindenberg. There was Chilboton, and who else had sites in Europe? I think that was it. That was the Clownet, original sites, I think. And there was no Antikythera, there were not a lot of things. And the ARM program maybe had like 3 sites fixed and just had deployed the first mobile facility in Africa, right? And we just had for first time airborne radar lidars. Now it's almost a common thing, everybody has that. So now things have been increased a lot. Now we have a lot of them, right? So what you see here is a photo of the ARM, the Atmospheric Radiation Measurement Program of the Department of Energy, super site in Graciosa Island, correct? It's an island in the Atlantic. It's been positioned there because it wants to study low-level oceanic clouds. So now we have a lot of sophistication. It used to be like a radar lidar and microradiometer. Now you have scanning radars, many different lidar systems, soundings, operational, aerosol sensors, all sorts of complexity. So the sites have improved since we launched NASA A-Train. The data set has been going on for 30 years. Actris is around, correct? So the Actris wasn't around. Now it's a framework. There's a funding. There's 35 sites. So things are not the same. There's not just anymore one NASA aircraft with a radar lidar. We have every country almost has an aircraft facility. There's a lot of opportunities, a lot of airborne sensors. So we want to, we want to take advantage of that, correct? In the cal valve of the EarthCARE, there was a call for cal valve. 30 plus countries responded. Greece was one of these places. This group is one of the participants of the cal valve activity. So there is a lot of opportunities to do that. Okay. Also, we know how to do that now. Back in the NASA days, when the NASA trained, we just were learning how the radar lidar works on the ground. Now we have standard algorithms, the Actris algorithms, things running continuously. You can go and download the data. Databases are available. So there's a lot of opportunities now to do a more systematic, and the network of sites is impressive. Okay, this is from the cal valve workshop we had in ISA in 2022. The stations with radars are in red, the stations with LiDAR are in blue. Of course, a lot of density in Europe, but there is data. Okay, of course, there is an asymmetry. Most of the stations, of course, over land, and most of them in the northern hemisphere. There's a sparse data set in the southern hemisphere, but we're building slowly capacity. All right, so this is what we're going to be using. And the data from the ground looks like that. That's a classical example of a backscatter LiDAR. It's as simple as a kilometer. I assume you're very familiar. These spots are liquid, and this is ice falling, and that's the radar units. Very complementary. The radar will go through, but you won't see the wimpy shallow start very shallow and very weakly reflecting. The LiDAR will see focus on the small droplets. The radar will focus also on the falling precipitation. Very low complementarity. So that's what you're gonna see from Pangea when you put your radar and the LiDAR. You're gonna have that. And then you're gonna be waiting for the satellite to come over. All right? And you hope to do a comparison between what you see and what the satellite sees. But there's not just a comparison, what we call location. Like you can say, hey, when you were flying over, you say from reports from EarthCARE, there's nothing, clear skies, but I did see clouds. So EarthCARE, not sensitive enough, for example. You can say EarthCARE saw only one cloud layer and missed two small ones here. EarthCARE doesn't do well in multi-layer conditions. So you're going to be doing a scorecard of different things. And the first thing you want to be looking is what they call feature box. How many layers you see? Was clear, cloudy, one layer, multi-layer, rain, no, snow, yes, whatever. All this information morphologically, what they call target classification will be the first thing you like to do. But I suspect you will be a little bit more ambitious. You like to do more things, correct? You like to do more quantitative stuff. Like you like to get all these properties. I mean, if you do microphysics, in the aerosols, probably going to go for aerosol optical depth, and you're going to go maybe for sizing information. And from the depolarization and the backscatter, you might go after LiDAR ratio, and then you go try to figure out what kind of particles, aerosol particles you have. Right? Well, maybe it's straightforward for the aerosol community, but in the radar, you're going to have something from the ground like that. This is a mixed phase cloud, reflectivity on the top, Doppler velocity in the middle, and the LiDAR will give you the backscatter. Once the LiDAR hits the cloud base, will stop. And the dipole, you can see very high in the ice, which falls below the cloud base, which is at 0.5 kilometers. And the green values is very low dipole, which means you have spherical particles. A lot of scientists have spent over 20 years trying to take radar, LiDAR measurements, microhydrometer measurements, distrometer measurements, all the synergy ground surface observatory exists to get all this kind of retrieval. This is the kind of things you like to know in a cloud. What the phase of the hydrometeors, how strong are the dynamics, how fast particles are falling, how much total liquid you have in the column, how much water, distribution of ice and liquid as a function of chi, and of course some dreamers, ice number concentration, liquid number concentration. The most difficult thing to get is number concentration. Okay? Guess what? Models love number concentration. Correct? So there's a mismatch of expectations. Models need to get right the number concentration to get right process rates to able to do small particles to big particles to make rain or not. Models need to get the number concentration right to even understand aerosol cloud interactions. But our sensors do not give number concentration. Right? You have to live with the fact that we see the big particles typically in that form. All right, so if I had to put a score in the quality, red means very poor quality, do not trust, and I will not trust it if you give it to us for Carval purposes. It has to be something really state of the art. But I will have more confidence if you tell me, Pavlos or Alessandro, EarthCARE says that the melting layer is at 4 kilometers, and we figure out the melting layer is at 2 kilometers. Actually, you misclassify snow as liquid. Then I will probably take the information from the ground base station because it's very reliable. As I said, location is something reliable. You can do that high resolution from the ground. But if you come and tell me your number concentration retrievals are not correct, I will ask you, how did you even get your number concentration retrievals? Okay. So these are the things that you would like to focus. These are a little bit more difficult, or at least more work is needed to convince everybody that a correction is needed, an adjustment is needed in an algorithm. All right? So that's what you're going to get from the ground. If you were doing EarthCARE, that's the satellite, you get something like that. I'm going to show you EarthCARE, I'm going to show you class of Calypso and models. Not very different, correct? This is the top-down view. The surface echo that was mentioned before by Alessandro and Lucas. And the LiDAR. The LiDAR, same thing. When it was on the ground, it was attenuating here, would not see go through. Here, it's attenuating below. All right. So in paper, looks like this is very complementary. We almost see the same thing, but except the propagation effects are very significant. For example, if you got a LiDAR here, this big convection, the LiDAR probably will have an echo signal near the surface and won't go through the system. The LiDAR here will go through, but extinct here. When you're in the ground, you don't see the surface. We see the surface. Okay? Is the surface a problem? It's a good thing for the radar from space? A bad thing? What do you guys think? Who says it's a bad thing? Raise your hand. 1, 2, 3. And the rest of the thing is there.
If you go out, it's a bad thing. If you do surface, it's a good thing.
Okay. Alessandro, is the surface a good thing or a bad thing? Both. Both.
Some applications you can also take advantage of the surface features.
Like
If you do repetitive overpasses over the same area, you can take advantage of the repetitive the surface doesn't there.
Yeah, we like that. We like that. The surface doesn't change. Very similar to what you said. Okay, so it looks almost like the compact should be straightforward. Why Lucas spent a year working on this orbital tool? Nobody knows. Why he would like to make this conversion upside down? Things look straightforward. We should just compare them, correct? They look very similar. The capabilities will be very similar. So we want to work on that. And so I'm going to talk a little bit on the surface. Okay? It's a problem. Alessandro explained, and you hit with something which is a 500-meter pulse in a round trip, but anyway, it's a kilometer. It hits the surface, and as long as this 500-meter pulse comes hitting the surface, it's like a mirror image of it comes back. So for the first 500 meters, you get an echo, even if it's clear skies, which looks very bright as the surface. So basically what they call a blind zone. You can't see anything. Actually, it's not 500 meters. For Klaus, it's about a kilometer. For EarthCARE, looks better. We will see. So the first thing is that if you're using observations from your ground station Antikythera, and you look at your laser, and the laser says the cloud base is at 300 meters. There's no hope that we see that cloud from space, because it's within the area of the surface so close that it's been blinded the radar, cannot see. Because of the reflection of the Earth's surface, okay? So as long as you have this pulse, the pulse comes, okay, it's already hitting the surface and it returns. As long as it comes back, comes down. For the length of the pulse, which is 500 meters, as long as you go down, it's a very simple way, there's a very strong echo because you're hitting the surface coming up. So it means that this part of the atmosphere, the first 500 meters, effectively as strong as the surface, which is the strongest target spaceborne radar sees. So it's totally what they call blind, you can't see. So although a radar says, for example, I can see minus 35, that's true above 500 meters. Below that, you don't see anything practically. So when you compare, make sure to remove the lowest kilometer clouds. That would be the most difficult to see anyway, because we're blinded, because of the surface return is very strong. EarthCARE will do much better than clouds. But this is something to consider, not try to compare coastal fog in Antikythera with EarthCARE. That's not possible to have. A lot of people ignore that. I would tell probably that I haven't seen literature, any paper, yet, after how many years? 18 years since clouds were launched, but somebody compared a model with observations and took that seriously. I think there was one we did in Cologne a few years ago when Vera did this in the Aerosol. She actually took the surface effect. But most people compare a model output and a cloud shot on EarthCARE without, and then when they compare the climatology from the model, they use all the clouds that the model makes. They should just ignore the first kilometer because we don't see it. If you don't do that, then you make the obvious conclusions that the model makes more and more clouds than the satellite sees. So that's the first thing. You have to be very aware of that. The surface is a very important thing in your Cal value. You have to understand we don't see it as well you will see it from the ground.
The question, it wasn't very carefully. You have that effect from the surface only from satellites or also from ground-based?
From the surface, from the satellite. From an airborne system.
Of course, from the ground, you may have clutter if you look with a horizontally, like for ground-based radar monitoring precipitation, right? Or if you look towards Athens, I will get all the clutter from the ears, because you are looking. If you look straight up, you will not have any. Yeah.
But as you mentioned, the surface is very stable, correct? So the surface This is like a system, and this the black line here corresponds to the surface area, top bottom left. Okay, the values are Alessandro's 48. You see, the surface is very strong. A W-band radar is not possible to measure anything above, let's say, 25, 30. Not possible. There's nothing in nature that would be more than 40. Imagine how strong is the surface, 48. You know for sure this is the surface, okay? So this is a very strong surface. If you look at the surface, the satellite starts from the left and moves to the right. At the beginning, the satellite has a clear path. There's nothing to obstruct the radiation. It hits the surface, it gives you a very strong signal. But then slowly, you see what happens. As the satellite starts getting into this convective system, you can see that the surface strength reduces. There's a depression. And then when the satellite, as a curtain, passes through this precipitating system, it recovers. So there is what they call a depression, meaning that the surface becomes less bright. There's a dimming of the surface. Okay? And this is very important because you can measure it. Using nearby values, you can figure out this depression. Okay? And Alessandro will be the first to tell you this is probably an incredible amount of information which you can't get from the ground unless you have something very sophisticated. This is basically the total extinction that the radar will experience once it goes from the top of this cloud all the way to the surface, two ways, because it has to come out to come back to the satellite. So this gives you the total extinction, which we call path integrated attenuation, total attenuation. And the cool thing about that is that although the reflectivity is the worst thing you would like to work in life, because the reflectivity of a radar typically, the reflectivity of a radar Z is proportional to the 6th power of a particle. This is really bad. This is not like the LiDAR, which is D2 square, D2 6. This PIA is proportional to the total mass, correct? In the column. Approximately. For simplicity. So per square meter you have in the column, total. This is extremely good. This is what something you're gonna get from a microradiometer, correct? If you had it, looking up. The only problem, if you're in the ground and a Medicaid comes over and repeat it, everything will get super wet because the rain falls on you. So when the rain falls on you, your LiDAR will die, will not go anywhere. Your radar will be wimped out and won't go probably more than a kilometer. And your microradiometer, that the Cologne is an expert institution, the radon will get wet, means the measurements are not valid. So you'll be doing measurements on something strong, but you cannot measure it. You can't penetrate, your LiDAR is dead, how many grams per square meter you have total hydrometers, you can't measure because your sensor is really wet and saturated, okay? Well, from the space, I can get it. From space, I can get it. So again, I'm not going to trust you. If you come and say to me, I can tell you how much was the rain for it. I said, I don't think you can say that about me because I know exactly the total amount of hydrometers I had in the column. And nothing from the ground can give me that. So also when it comes to rain, the surface observatories of actors will not be really our standard. If somebody now do the effort to use weather radars, which we don't have here, weather radars that we don't have in many places in Europe, but actually combine to use weather radar columns, maybe I start believing more of that. And that's what they do in the US, correct? They use the next one. So be aware that that's a tremendous advantage of having a spaceborne radar. So that's another area which we have. It's going to be difficult to validate the rainfall rate retrievals of EarthCARE, using, let's say, an actress type of instrumentation, or whatever you're going to have in PanCare. This will be very difficult because millimeter radars from the bottom up, they won't get wet and they will not go through. You're never going to see what we see. And you don't have a good constraint about the total water in the column, which I have easily, effortlessly almost, by using this reversing technique. So the surface is a blessing in this and a problem because it blinds the noise level, right? And the other thing is that the low level blockage. That's what you will measure. That's a better example. This is what you're going to measure from the ground here. Your red line will be your light laser, and the color there will be your radar. All right? That's what you're going to measure. But that's what you're going to see from space. This is what you measure, and that's what you're going to measure underneath actually from space. All right? So you see First of all, everything from space loses stress vertically. Why? When the ground looks very high resolution, nice structure. You see, there's a little bit blocky. What you see from space looks like blocks, like maybe 3 pieces of information. 1, 2, 3. Well, ground, you look like you have very nice information. You're back? Okay, why? Resolution is wrong. Resolution. So what's the difference in resolution? When you have a ground-based system like a radar, the resolution vertical could be 30 meters. 30 meters is high resolution. What's the resolution of EarthCARE?
Depends on the product.
Let somebody else answer besides you. If I want something, I will ask you.
Guys, but you don't decide, you have to inquire. Because,
You block. Hello? I mean, you want to go to EarthCARE Calvan. What's the resolution of the EarthCARE CPR?
Yeah, but this is depending on the product, in the
Depending on the product, what do you mean?
for example, for the other products, they are.
No, we're talking about CPR.
5 liters, 333 meters,
Eh?
333 meters.
300.
Are we guessing here? It must be a specific number.
That's it,
You've been participating in EarthCARE meetings like every other day.
That's it. When I see the products, I will remember.
I'll make a note about that. So what do you think is the vertical resolution of EarthCARE? Anybody knows? Lucas, what's the vertical resolution of EarthCARE?
Around 100 meters.
That's a different thing. That's the sampling.
Yeah.
Yeah, okay.
Do you have a better marker? No?
There are some working.
Yeah, so you guys don't have these issues with the LiDAR, right? Has ever been the range resolution a problem for the LiDAR? I mean, did you ever question if you want to have even better range resolution in the LiDAR?
What is the resolution of the airplane?
Vertical neutrality.
Vertical.
Yeah.
Lower resolution.
What do you mean? Fine.
It's 100
Range.
It's 100 meters, 500 meters, depending on the altitude, 1 kilometer.
But we're talking about the healthcare line now.
So, okay, let's do this.
What is mentioned before is 300 meters, and depending on the product, depending on the altitude, again, 100 meters of product.
300 meters? So much?
Yeah, yes.
Okay,
Now it's really 30 and 60.
30.
let's say this is a cloud, it's 100 meters thick. What percent of the clouds you think are less than 100 meters thick in global? How often you see clouds which are 100 meters thick?
National players.
Hmm?
Super players from the event to them.
What percent of the clouds are, let's say, what percent of the clouds globally are less than 500 meters thick?
The marine clouds, a big percentage, all the marine clouds.
Okay, what percent? 20%, 5%, 50% of the clouds are
10%.
50%. 50% of the clouds from climatologists are less than 500 meters thick. All right? So let's play this exercise here since you want to do the interpretation. So I will make it 2 clouds. The one is 100 meters thick. The second cloud, put it with a different color. I'll try green. Not my favorite, but I'll use it. Let's say a thinner cloud, which is only 20 meters thick. Okay? And for all purposes, the reflectivity is plenty. The reflectivity of both clouds, let's say, is very strong, -10, very strong. So Alessandro will not raise a question you might want to raise. How this cloud will look from space?
Can the cloud be 20 meters?
Yes. A lot of them.
You get something in average, something in between.
A satellite comes, sends signal, and it will give you something like that, okay? How, when you actually, you're in Pangea, you have your sensors, you have everything there, how do you think this cloud will look like? From the ground, it will look exactly like how you see it, because you're gonna have your little laser, radars, high resolution, everything. That's the ground.
People are taking the resolution. What we say was the resolution of the satellite.
CPR, which nobody should forget, resolution is 500 meters.
Of the products.
No, the products, the resolution of the radar.
Why Lucas said 100?
Because I was confused.
No, he.
It will show like a 500-meter cloud.
Correct. It will look like a cloud which is like that. And it will look, it doesn't matter if they agree, all of them will look like that. Right? Because the system cannot say better. All right? So first of all, don't call us also to tell us that the clouds we make from EarthCARE are fatter than the ones you see in Pangea. Okay? Because they will be. Everything that we see from space are stressed. Why we did such a horrible mistake, putting such a long pause, when we know that at least half of the clouds globally are not even 500 meters? Why would we decide to put 500 meters as a resolution from space? Why wouldn't we do the clever thing? We've been having our actors for 2 decades. We know how the clouds look like. Why wouldn't we make our poles to be 50 meters? So we don't create stress clouds vertically. No money? No power. I was going to say the opposite. With a lot of money, you put the 500, but anyway. That could be finances, could be financial reasons, could be one of them.
Is it a compromise with the frequency that you work with?
Actually, all the radars in space, they all have 500 meters. I don't know why I have this conspiracy of resolution. Any other thought? Why somebody will put on a radar a long pulse? What a long pulse give? When you put in a LiDAR long pulse, why you put long pulse on a LiDAR?
Well, we don't have enough signal to measure.
Oh,
Okay. But I don't like for radar anymore. So.
Right, the same thing.
so you know how they came up with the number? They said, we want to make EarthCARE minus 35, correct? They said, that's our my transmitter. How much has to be along the pole? Like the same way you did a LiDAR. And they figured out we have to be 500 meters. Let's make it 500 meters. That's how close that came up. They said we have to hit minus 30. What do we need to do? So you are starting with a notion, a target, and then you put it. Now, so the 99% of the scientists, they're very happy that EarthCARE has changed their minus 36. All right? But you should know that this comes at an expense. This is one of the expenses, that it comes in very coarse resolution. It will make a lot of these very tenuous clouds in the boundary layer to look like stress. Not only the clouds are stressed, I was talking about the surface. When this pulse hits the surface, the pulse comes here, then the pulse is here, the pulse is here, and keeps going down virtually. At the same time, as long as it hits, the same thing is come back. So basically the surface elevates, the whole thing is blanket. You don't see anything. This is what you see there. This is bright yellow. Is the surface is not the zero height here, it's elevated because of the surface there. So you see, when you compare a thin boundary cloud, which is typically what you're going to see in Pangea, okay, the clouds look dramatically different because we don't have good skill in the lowest kilometer, and we don't have a good skill in reproducing fine structures.
I have a question.
Yes.
So the 10 watts per meter that the care could resolve is anywhere but except of the sea. So it is like.
Can't do the 10 watts per square meter in most places because of complexities, but it was a good goal as a closure argument. Why you want to study? You said if you want to understand climate and climate change, you understand radiation. To understand radiation, then you understand enough clouds precipitation and aerosols. So he said, if we give you the sensors to measure them very well, you should be able to produce the radiation on top of the atmosphere within 10 watts per square meter. So as a scientific argument, that was one of the foundations of why we launched EarthCARE. Okay, we want to really prove that to ourselves that we understand enough of the interaction of aerosol, cloud, precipitation, and radiation to reproduce the top of the atmosphere within 10 watts per square meter. It was an argument that put together, okay, and then we said, if this is the goal, what do I need to measure to make it happen? And then they said, we need a radar, we need a LiDAR. That's how the mission was built. On an argument for a closure for radiation, what sensors I need to do to be able to do that.
But remember that the closure is at the top of the atmosphere, okay? We are not doing closure at the surface. radiation closure at the surface, right? Because the radiation closure at the surface is much more complicated if you have a space-borne system, because as you said, you're not capturing the cloud base, which is critical to do radiation by the surface. But
Yes. On top of the atmosphere, yes.
it's fine. It's fine.
Clouds will be different, okay? Clouds will be different a little bit. Some properties, even the feature mass will not be the same. The cloud will look always thicker. What else will happen? The clouds will look thicker and they will also look something else. You can't make up, if you can have something which is 100 meters, then stretch it to 500 meters. It will not have the same reflectivity, all right? So basically almost like a filter, you reduce. So the reflectivity will be biased low because you're using gaps really and an echo, and you're giving an answer which the radar assumes that the echo fills everything. So all the reflectivity will be a little bit lower, all the clouds will be a little bit more stressed. So that's obvious, and the surface will be blind. So these are the things that you need to be aware. That's pretty much will be a limitation.
Yeah, question. If now it's already decided 20 years ago how you the measurements, but one could decide to have high resolution measurements and then create different type of products, high resolution and low resolution, for example, like Calypso or Calypso, depending on the averaging then later.
No, Klaus and Calypso, they are fixed. Klaus has a fixed.
But Calypso doesn't. So we do have like average 80 kilometers at 40 kilometers at 20 kilometers and at 5 kilometers.
But that is
So that's a long
track.
It's a long track.
I'm talking about
In an aerosol layers, typically when you see African dust, they're not like intermittent. You don't have an aerosol layer which is 3 kilometers propagating. A cumulus cloud low could be a kilometer moving. So when you do aerosol, nature is more gracious, it correlates much slower, so you can really stretch the average. You can actually average 60, 100 kilometers, and you can assume that all I do is I increase my signal to noise ratio, the layer is that long, okay, it's that extensive. If you can't do this really trick with the clouds. Clouds are very intermittent, you cannot really stretch a long track too much.
So, okay, vertical, for example, Wyvern will have also 500 meters vertical
Yes.
beginning.
Yes.
Okay.
Yes.
Because it has to do what with a spread of the Doppler that we want.
No, it's for the same reason we want to have sensitivity, and therefore, basically, the question is very good in the sense, ideally, we would like to have, for instance, change the PRF. Sorry, not change the PRF.
The pulse length.
Take the pulse length, so that we can do instead of 500 meters, we could say, well, we up the pulse length, we go to 150, right? Now, what is the trade-off? If you go to 250, you lose sensitivity. Okay, you lose a factor of 4, goes with the square. Okay, so if you half, you lose a factor of 4, so 60 dB. But still, we were saying, why not doing that? Because in fact, minus 37 dBz, minus 36 dBz is already amazing. If you lose 6, you go to minus 30, it's still amazing. But unfortunately, this is what it is. They cannot change the pulse length in the EarthCARE.
Future radars, though, they will also have all the missions we'll be thinking now and for the future, they all have multiple ports at the same time. So future radars will transmit, the typical radar right now, like LAVSAT, sends the ports and then comes down trip, and then the second one comes, etc. In the future radars, we're going to have ports will be like this is going to be transmitted. A very short pulse, an intermediate length pulse, and a super long pulse. Could be like 10 kilometers pulse. Could be 2 kilometer pulse and 100 meters pulse. And this will be coming, hitting, and it will be giving 3 different views. And a super high res, but low sensitivity. Intermediate resolution, but better sensitivity. Very good sensitivity, but not capable mostly very close to the ground because of this response of the echo. So in the future radars, we're designing a lot like that.
And Wyvern, why not?
Because the Wyvern is, it's part of the Dragon legacy systems. There's the white dragon, which is the EarthCARE, and this is going to be probably a red dragon, meaning it's a legacy system. You use an old transmitter formation, which you cannot do these cool things. Like you're building the new LiDARs now for the group. The new LiDARs can do a lot of capabilities. But for space now, this is pretty much mature now. We can do this, but not for wider.
So the vertical resolution is not only dictated by the pulse, like in another looking radar, but also by the beam width of the system. Because imagine you are looking slant, certain aperture, so this dictates the vertical resolution as well. So somehow with the antenna that we have, basically the size of the antenna which determines the beam width is already, we cannot do better than 500 meters. So we could have a pulse which is much shorter, but basically this will not benefit in terms of vertical resolution, because then in that case the beam width will.
Now, granted, all the products of EarthCARE will come with a vertical resolution of 100 meters. That's not true resolution. We oversample by a factor of 5. Okay, the actual resolution of the sensor is 500 meters, dictated by how long is the pulse. But the data will come oversampled by a factor of 5, which I tell you, it does have some benefits, but you cannot, avoid the fact that all clouds will look stretched and patterned.
Okay, last question. So in the end, there will be, you will have in the array, there will have data 100 meters, and then you will have the same value in 5 consecutive points. No, different.
Yes.
But then this 100 meter will be represented for the plus minus 450.
500.
Okay, plus minus 500, plus minus 250.
Yes. Yes.
Thank you.
All right, so I want to spend a little bit of time to explain the Doppler, right? So this is a new thing that the EarthCARE does. Why do we need Doppler from space? Already been said about that many times. Alessandro spent an hour explaining to you why Doppler is useful for the horizontal events. What are we going to do with the EarthCARE Doppler? What you would do if you had EarthCARE Doppler? Has anybody worked with Doppler here? Doppler LiDAR, Doppler radar, Doppler.
Only product wise, we cover the Aerosol and line.
Okay.
What's in the wings?
So when you're looking with the LiDAR length,
Line looking vertically, you see the wings, both horizontally and vertically.
Yeah. So
Problem updraft, downdraft.
in paper, the first thing you will say is we can measure updraft. How strong are the convective motions? How strong in a thunderstorm the air goes up, all right? So the first thing you understand is how difficult it is to do that. What do you think? What's your feeling? Do you think we have, after having radar since the 60s on the ground, 70s, 80s, having satellites, having all these sensors, how well do we understand these updrafts in convection? These convective cells are really, we see them everywhere. Some thunderstorms you have here in Greece, okay? You see hailstones, you see all these events. How well do you know? How big is our database? How well do we measure these convective updrafts? How you would do it on the ground, if you were from the ground? Now you want to do it from the space, but the first question is, have you done it from the ground? How well have you done it? What exactly doing it from space will give you that you don't know already? If you want to sell it as a mission, if you think the Doppler is the capability that this mission is selling, it must be doing something that the ground cannot do.
Global coverage. Then will be.
Global coverage. It's an excellent point of every satellite measure. Especially, you can't measure anything over the oceans. All the radars, everything we have is on the ground, over land. So having global coverage over the tropics with a lot of convective cells, that's important. So expanding the climatology. But what about over land? How do we measure the convective updraft over land? Let's say if you see a thunderstorm rising, in Athens, going up 10, 15 kilometers, and you see lightning and everything and heavy rain. How do you measure that thing there? With
The Doppler.
Okay, with a Doppler. How are you gonna do that?
When it rains, there is the ground is radar blind, so.
Yes. Your millimeter radars will, they will, let's say, be challenged, won't go through. But the weather radar, you're getting also an X-band, it will probably go through. Okay? So let's think about it. This is your convective form. Big updraft. Okay? Rain underneath. Where is the best location to put your radar to measure this updraft?
Doppler radar.
Okay, we are on.
Okay, for which side? Left, right?
How is it moving? It looks like continuous to me, correctly.
So you would put it here? Put a big radar like that here?
In front. Put it in front of the other side.
Okay. Same. So you would put like that, what I am doing, and measure the Doppler here, all right? What the radar will measure?
It becomes calmer.
Okay, let's focus on this point and we'll discuss. So at this point, what are you gonna measure? What goes up? W, air, right, goes up. What goes down? Sedimentation, particles are heavy, they're falling down. Anything else? So basically, it's just a projection of those two that determines what I'm gonna see. Anything else that will contribute? Horizontal wind. Also, which also projects. So, what do you measure with a line of sight? For exactly what Alessandro's wiring will do, it will be three components. Part of the sedimentation, projected to the line of sight, the vertical air motion, and the horizontal wind. That's difficult, right? You can't take these three. First of all, you need to know the horizontal wind. Index flow. You have to know what kind of particles you have. Not well known. What will be a little bit better geometry for this? Vertically pointing, mobile track.
Yeah.
Radar vertically pointing, running around, cutting on the hill, go to the storm, okay? So you're looking up. What's the advantage of this? If I'm looking.
Don't have the width component.
Correct. So I only have two problems then. I only have this and this. And then you have to play, this is a retrieval. You have to do your best guess. Okay? You measure V. It's the addition of the air plus the V sedimentation. You will make some guess for the sedimentation as a function of reflectivity and temperature, if it is solid particle or liquid particle, if it is high reflectivity, low reflectivity. You have a guess and that will have a delta, an error. There will be an error here, and then the air motion will be retrieved, okay, by taking what you observe minus the sedimentation, and perhaps you're going to have a delta, which comes how well you know that or how well you know that. Right? If you're on the ground, this has no error. Doppler is the best measurement a sensor can do. If it hits the ground, it's not moving. Doppler is the best measurement a radar can do. Much better than reflectivity, power, polarization. Doppler is the best measurement can do. So if you're on the ground and you have a good mobile unit and you go underneath the storm, you might get an errorless estimate of the Doppler. If you have an educated guess, this might be a meter or two a certainty. That means you can actually get the vertical air motion within a meter or two. Okay? That sounds a great observing strategy. You know how many times we have done that? Ever. All right? We have, with mobile vertical pointing, no, we haven't done. But you might think of other ways. We have tried things like fixed radars, like you send an indicator, you wait for the medicane to come. Okay? It will happen. It will come. You collect the data. You put it together. I can tell you that globally, we may have 100 updraft captures in 50 years. One updraft, 100 snapshots. Think about what the snapshot is, okay? When you have a convection, convection doesn't get born as a thunderstorm. Convection gets born as a little cumulus, deeper cumulus, bigger cumulus, cumulus that goes and then dies a little bit and then revigorates. I can tell you one thing, you take any model output of any cumulus cloud and you look at the W, just from one life cycle of one cloud, you can get all possible Ws. In these strategies, waiting for things to come over you, you almost like you are waiting in a photo booth. Eleni comes in, says, can I pass? Yes, he doesn't ask, he comes in. She pressed the button, I get a snapshot of Eleni, and she moves on. And then as a modeler, you're asking, try to understand how that evolved just from a snapshot. Basically, you want to understand all the history of a lane by just a snapshot, something that came over you. You understand the sampling is horrendous. You only get a snapshot of something which says dramatically on an individual cloud, when at the same time you might have hundreds of them happening. So getting statistics is impossible. Space would be looking down, so definitely doesn't have the horizontal wind, less problematic than the wide wind that has to figure out the horizontal wind too. And looking down, and I can tell you, yes, we can do an indicator here. So space has a chance to do that, correct? Keep flying around and you're gonna hit eventually storms, all right? So we think with EarthCARE, you will be able to do that.
But you are only only 3 years. This is limitation of the mission.
Yeah, we're gonna get probably
How
a
many?
few thousands of them.
5,000.
Yes.
And with the Weaver, what you said before, you go so like that.
That would be very much more if we get to the point. The second thing that you would die with radar is to get how big the particles are when they fall. You see this? If the velocity is 0, it's cloud droplets. Cloud droplets don't fall. Clouds are suspended effectively, okay? They're not falling. If it's falling with 1 meter per second, 2 meters per second, it's liquid, it's drizzle. If it is between 1 and 2.5 meters per second, it's snow, it's sub-zero temperature, snow. If it is falling with 5-6 meters per second, it's big raindrops. So if I can get a Doppler, I can get something about the size of particles. So that's great. You don't have this information globally. Okay? What's the problem? In convection, the question is that remember the geometry, you see two things. You don't see just that, you also see that. But in 99% of all the cloud layers precipitation we see globally, the WR is practically 0. So everything you measure most of the time with EarthCARE is how fast particles are falling down. Convection happens in a very small fraction of space. It's less than 1% where the W is so strong. So EarthCARE will do much better to get particle climatology fall velocities, which is important for models, very important for models, much more difficult because of its sampling to hit the right spot of the cloud at the right time to get an answer. All right? So that's the other problem. But Alessandro says that that's why the sampling matters, because with Wyvern can do it 50 times more faster.
So EarthCARE will not be able to give you information about the convection, but Wyvern will give you. That is the.
I said that you're gonna get some of them, but it will be very frequent you're gonna hit some.
And it will be difficult to separate it. So if you have a system, or would you be able to separate it to understand that this is convection?
Good question. Good question. No, we can separate it. How strong is the updraft in convection? How strong updrafts can be? The ascending motions in cloud. Who's good modeling here? Yes. 5 meters per second would be a wimpy updraft. Yes, over ocean, not gestus. They can go to 30, 40, 50. We have never measured any because we have never been. In an aircraft also you don't penetrate. So you cannot penetrate with an aircraft. You have to get extremely light with the profiling, and every technique we use, multiple radar, multi-Doppler kind of things are not really good. So we really don't have a good, we don't know anything about convection. That's the bottom line, right? So you asked this question. So in convection, you can guarantee that the air motion is much stronger than the sedimentation. In everything else, which we call stratiform, you can assume that the air motion is practically 0. So what you measure in stratiform is the sedimentation directly. That's what we have our algorithms fine-tuned right now in EarthCARE. Because we know 99% of the time we're going to be looking at just particle sedimenting. So our algorithms have been fine-tuned by that. Now we have to work with Alessandro on trying to figure out when we get to 1% lucky to hit a strong updraft, how to estimate the air motion.
And then if the updrafts are in the convection, you have updrafts and downdrafts, one next to another. And depending on the size of the
Yes.
Some of these will not be like
Yes, of course. You're absolutely right.
Yeah,
I think with EarthCARE has the narrowest sampling volume than any other spaceborne radar we have for.
Okay, so it's the best.
Nearby other thunder has the best chance to separate them as it transits, right? So that's a great point. All right, this is how the Doppler works. I want you to follow this. This is very important how the Doppler works. Now, this is an animation for a very good friend of mine, professor at McGill when I was there, Frederick Fabry, a bright minor in meteorology. He's still at McGill University, and so these are particles, right? The particles, the same particles, no particles come in and out. The waves are hitting the particles, you see the particles are moving. The combined backscatter from the particles is shown here. This is the output of the return backscatter signal. The number of particles is the same. How strong is the return signal changes? Why? Because of the? Okay, so it's constructive, destructive interference, correct? So that means if I use one pulse, hit a cloud, most I will hit the right answer. So in radar, we throw pulses to get to that. That's the first thing. The second thing is the Doppler. So some of these particles move towards the radar. Some of the particles move backwards of the radar. Okay? But the radar and EarthCARE will only give you one answer. It will give you one value. Okay? This value is representative of everything that happens here. Okay? There's a lot of things moving. So maybe everything is moving, let's say, because of the wind with 10 meters per second towards the radar, but things are going a little bit backwards, forwards. Some things are going with 12 meters, some things going with 8 meters. So there's a lot of spread. There's a lot of variability in the Doppler, correct? There's a lot of turbulence, a lot of things going up and down, correct? So this is what you're going to be measuring. So here you are, you have your sampling volume, you happen to have a lot of particles.
So there is a red marker.
Yes. So if that's your resolution volume, perfect. This is your resolution volume. We have all these particles. You know, listen, the particle will be identical, exactly the same size. All the particles have a sedimentation velocity 1 meter per second. Okay? But then within that volume, you could have, first of all, an air motion. The whole thing goes up with 3 meters per second. So this goes up, this is going down, right? So if I was here in what Alessandro was trying to see the velocity space, okay, so this is 0. Where would be the Doppler velocity of this combined thing? Up or down? Up. So if this is, let's say, positive is down, so we don't get confused, and negative is up, okay? You will expect a delta function here at minus 2 meters per second. We agree with that? It's the combined effect of the 3 going up, which is negative, plus 1 going down, minus 2. But this is this air going up. But within this air, there's a lot of turbulence. Okay, so the particles are going a bit faster, lower, they're moving a lot. What do you think is going to happen? Instead of having this delta function, it will look like a Gaussian spread. All right, we understand that? That makes sense, right? You see that was on the Doppler, on the line system. Okay, so this is the broadening. If you do HSRL, it's like, you know, the Rayleigh broadening versus a mean. So this is the broadening, okay? So that's how the Doppler content looks like. EarthCARE will only give you the red line, will not give you the spread, right? So what can make this to be spread? The particles are identical. The spread will be because there's a lot of movement, but the spread will be just because I have big drops and small drops. So if I have big drops, the big drops will actually be going farther down. So maybe the big drops will be here, the smaller drops and the smaller drops. So it will be just, you could have broadening just because you have different sizes. You could have broadening just because you have a lot of turbulence. That's all healthy. We love this. who love this broadening, all right? Why you like broadening? You will understand because you try to measure something, you like to have a little bit of the correlation. So now you understand the Doppler spectrum. This is what I was doing. The signal looks like that. It has a peak, but a broadening. The broadening could be microphysical because of particles of different sizes, but the broadening could be just purely dynamical, just because I have a lot of turbulence. All right? So this is very important for Alessandro when he was trying to do this from space. Because if you understand a little bit about power spectrum, the power spectrum can be also have a autocorrelation function, which is here. So basically what it says to you is the following. So the more narrow the thing is, follow me here, the more narrow the thing is, the more everything looks like it's falling in place the same. There's no variability. Okay, everything's falling exactly the same, there's no variability. The more wide it is, the more chaotic are and the more decorrelated the whole thing is. So you look at the snapshot, you go the next millisecond, it has changed already. So you don't want these things to be too wide, because if it's too wide, then you're measuring it, but if you don't measure super fast, you lost completely. And when you measure Doppler, you need to do what Alessandro would say, correlated measurement, very fast in time. How fast in time? Well, tell me how broad that thing is. If it is very narrow, take your time. If it is too broad, as fast as you can. But Alessandro was just saying, you can't go as fast as you like in space because you have to let the parts go into the atmosphere, come out, and then the next one. So that's the problem when you have to go to polarization diversity. So this needs to be, so let's look at EarthCARE. How broad is EarthCARE? What do you think EarthCARE will be? Why EarthCARE will be different, the broadening, from the broadening I have from the ground. Because on the ground, the broadening comes from different particles creating stretch microphysical, or different dynamics creating stretch dynamical. Well, it's the same atmosphere, I'm looking from the space. Why the space will be different? If it will be different, might be actually the same. That's what they were thinking back in 2000.
Is that happening?
Yes.
Okay, the satellite moves so well. We talk about broadening. Talk about broadening, correct? Think about so the satellite is moving. What is matter? Yeah, okay. It's eager. Okay, so let's look at this, okay? First of all, how the Doppler happens. The Doppler to happen requires two pulses, all right? So when I'm here, I'm hitting Kelly. The pulse comes back. I have no information about Kelly's motion. If I send another pulse to Kelly, and Kelly has moved slightly to me, the time it would take or the phase that Alessandro was there would be slightly different because the path is different. She moved towards me, I can see her moving. She moved a little away from me, it would take longer for the second time, I would know she's going back, okay? So movement to get, I need two pulses, all right? Not in EarthCARE. In EarthCARE, I can have movements for different reasons. So here's the pulse of EarthCARE. You see it? EarthCARE is flying, that's the footprint on the ground, and that's a target. When I say target, is the observatory here. This is the astroscopio. It's a building. Is the building moving? No. Good. So I'm setting my first pulse. I go distance R1 and come back. I clock it. Now I'm setting my second pulse. When I set my second pulse, I have moved. The satellite have moved. So I'm clocking R2. The building did not move, I move. I made Doppler for the building. So I don't have to wait on EarthCARE for the nature because of microphysics and dynamics makes broadening. The platform makes broadening. It can make everything move, even if it's on the ground. Everything moves. Everything which is ahead of the line of sight moves towards the radar. Everything which is behind looks like goes away from the radar. So EarthCARE creates a lot of broadening. The more the broadening, the faster you have to sample. Otherwise, you lost it, okay? It's almost like the same thing said that the more the broadening, should not let the antenna move that much before I hit the second pulse. I should be doing the pulse so fast that after the distance between R1 and R2 is almost zero to make that this actually hasn't moved, all right? Well, that means that the spectra, rather than being in nature and from the ground will look like that, the Doppler spectra from your radars, you want to do secondary eyes, the multi-peaks and everything, From the ground, look, you will see multi-peaks, you will see narrow spectrum. From space, it's a pretty wide spectrum. Effectively, the signal, the measurement is high. Because of the platform motion alone, there's no movement of particles here. Just for the motion of the platform, I create an enormous amount of broadening, and I cannot transmit that fast to make a good measure. As a result, the Doppler from EarthCARE is very noisy.
This cannot be filtered because we know the velocity of the satellite. So,
It has nothing to do with the satellite velocity, unfortunately. So this creates enormous broadening. Now, okay, but there's a good thing. It's broad, it will be noisy, but it's unbiased. Okay, it is very wide noisy, but the center is still that. Not really. That's the problem. That's if the target is the same. Imagine the target moves. This is the target. I'm moving to the target. I see it coming towards me. Once I pass the target, it looks like it's going away from me. But the target is the same. So basically, it has the same response to me. It looks like I have something heavy in the front. But what if EarthCARE moves to an environment like that, where the forward target is much bigger than the backward target? Okay? This part of the beam, which is forward, is saying to you, I'm going up. And this back part of the beam says, I'm going away. But they don't have the same strength. They don't have the same strength. None of them is moving. They're just different scatterers. So it makes the Doppler look like it's going up because it's not balanced. It's almost like skating. Skating and you're hitting the pavement. Once you hit the pavement, you go forward, correct? Basically, EarthCARE will fly, and once it hits a cloud, there will be nothing below, but on a cloud in the half beam, it will look like it's going up the Doppler. Once exiting the cloud, it will go down the Doppler. So the EarthCARE Doppler, if even no cloud was ever moving, it will create up and down, up and down, up and down, up and down, just because the reflectivity changes. It will go, the reflectivity ahead of me goes up, I'm going towards. I'm exiting the reflectivity, I'm going up. So if you look at the Doppler, it goes up and down, up and down, up and down, complete mess. So it's very noisy and highly biased. But we have done a lot of corrections over the years, correct? So we have done a lot of corrections for that. So now not only you're broad, but also you're biased. So in the EarthCARE algorithms, we correct this bias. We do a lot of averaging to kill the broadening. We do special techniques. We do a lot of techniques. And I think we have it under control when the antenna is pointing where it's supposed to be pointing.
Can I ask something?
Yes.
Since you know your velocity and how are you biased? Since you know how you travel, let's say, and you know your movement, how you cannot take this into account to correct?
All we know that the velocity, you have to understand what it does. The velocity movement create apparent Doppler to the particles. So create a broadening, basically a decorrelation. The end result for me is that the signal I get every time I hit it with a pulse, every time I hit the pulse, I try to get a response, and from pulse to pulse to see the faces. Because I transmit the pulses so slowly, because of the constraints of the troposphere, that means by the time I hit it, the next time it's so decorrelated, I cannot really get a grasp of what was the Doppler. It's very noisy. So I know that this will be broad, and all I know, that's all I know from the velocity. But how to correct it, the damage has been done into the time series data again. Okay. So, but the second part, this can be correct. This bias can be correct. Because the bias is a function of the reflectivity gradient, and that I measure along track the reflectivity. So if I know how the reflectivity changes, if the reflectivity ramps up, I know it will create Doppler bias up. If the reflectivity ramps down, I know it will create Doppler bias down. And we know how to compensate this very well. Right?
Why the reflectivity could be neither going up, neither going down, how the satellite goes by?
There will be no bias, that will be uniform. But if you ask Alessandro, that never happens. And that's so correct, never happens.
I have a question. Since you create this broadening to your movement, to your platform movement, any broadening happening then due to particle microphysics or different velocities that is shorter than this broadening. Can you see that?
No, because the total broadening, we do measure something which we call sustainable products. You'll be getting what they call the reflectivity. Okay, that is better. You're gonna get the reflectivity, the infamous, which Klaus was giving you. You're gonna get in the VD, which we're gonna be doing a lot of filtering. What you're gonna see is after really, literally ironing the Doppler to be right. So you're gonna get the V Doppler, and then you get also the sigma D, which is basically how broad the spectrum is. Okay? But the sigma D is the sum of squares. Okay, so it's the sigma due to platform, the sigma due to turbulence, the sigma due to DSD, particle size distribution changes. All right? This, in normal conditions for EarthCARE, should be, let's say, 0.2 to 0.5 meters per second. This could be anything between 0.2 to 2 meters per second. All right? So this, simple math, I can tell you it's 0.3 times the velocity of the satellite times the 3-degree beam width of the radar. That is 3.6 meters per second. This matters not. If you do 3.6 square and you add those two, still you're gonna get 3.6 square. So because the sum of the square, you don't see any changes because of that. This dominates everything.
Right. Once you correct it, then you see others.
No.
No, because you can never go that good.
Well,
Although we have seen some,
yeah, people that they can.
yeah, some people have, but we use it most as a quality control for us, because if you exceed certain values, then we know that we have to do certain work. So the Doppler from EarthCARE is very noisy because the platform motion, not so much how the uniform beam feeling, this we can correct very well. The platform motion creates the Doppler content of the volume to be very broad. And that creates a very fast decorrelation of what is happening. And that decorrelation, because we're not something faster than to handle it, creates a very noisy Doppler estimate. To overcome it, the only way to beat noisiness is to average. So we average vertically, we average horizontally to give you something that looks good. And I think we have done a good job relatively on that. So you saw the big silent features here, the Doppler. There's nothing one-to-one to compare. It would be very different, but Lucas' product, though, can take your Pangea data set and make it look like EarthCARE. It has all these effects.
Before the correction of the
It
broadening.
will give you something after the corrections. So basically, it will tell you how will be the best estimate. Lucas' idea is to give you something you will get from the level 2.
Yeah.
It's not to generate to you raw data to play with algorithms to correct. It will tell you what you will get from EarthCARE and what you should be getting equivalent. So Lucas' product will tell you how the surface echo, the blind zone, and the Doppler has to be manipulated. But the Doppler is what we have seen. I mean, I have seen some data that it looks pretty promising.
One more question. You mentioned before that from the attenuation, that you have the attenuation from the surface that returns back to the light, and then you can do the calibration. The fact that you have the attenuation, you measure for
This
the
is not
rate
for the attenuation. We use it as a signal to figure out how much, for how many grams per square meter in the column. Basically, how much total hydrometer we have.
I mean, if you use this, and you have some we collect the 500 meters where you have the low marine clouds, then that means that you attribute part of the water vapor in the other
It's
cloud.
not water vapor, we just hydrometeors. The water vapor we correct already because we know from reanalysis the humidity. That's already been taken care of. We talk about hydrometer induced attenuation. Listen, Alessandro can tell you that often because of the blind zone, you don't see the cloud, but in the depression of the surface echo, you can see actually there was a cloud because something attenuated.
Okay, and then you skip this measurement.
For calibration. Calibration also happens always in clear sky. In a lot of parts of the oceans, in Southern Ocean, in Southern Pacific, North Atlantic, there are basins where actually there's often very clear conditions. We can use those to do calibration. So don't expect the calibration we're going to get it from because they're well established. Doppler, we would do it ourselves. We don't need somebody to reservoir off, because you know why? Because you can't see it here. Correct? The Earth's surface, when we have the final product, has to be going with 0 meters per second. We can't be making the surface going up or down. So when we produce your product, we'll be consistent that the cirrus clouds are not going up 20 meters per second, everything's sentimenting, and that the surface is 0 over an orbit. We're expecting an orbit, the satellite will be wider and going up and down, okay? So it means that over an orbit, if you look at the Doppler surface, will be moving up, down. We're actually doing fits, we try to correct, we do all these corrections, but at the end of the day, everything we know about Doppler will be consistent with it. So this is part of the algorithm correction. So Doppler, we will do it from space. Calibration of the radar will be done from space. Here, the main thing is to tell us how much better can we do near the surface? How many grams we missing? Still, we think we do much better, but there's room. How much we do better in ice properties, liquid clouds? If you have a nice multi-wavelength facility, a lot of sensors, you can do some quality retrievals, but over a period of time, then you can have a very good data point and say, listen, I've been doing that over Antikythera for 2 years. Your product in the Aegean sucks. It's producing double the water content I see from my retrievals. Fix it. Okay, so when you get that kind of data over a period of time, good quality, then it will be, you will have an impact on the caliber.
And that's why we need the network, because it's,
Yes, that too. Because Lucas will tell you which part we're not gonna see anyway, so you don't bother. Basically, Lucas will tell you, I will remove for you the first 500 meters because you're not gonna see it. He will do that. The tool does that. He cleans it out the way we did from space.
also, yeah, but what are the
Yes.